For all of human history, we have charted what we can see. We connected the brilliant pinpricks of light above us into gods, and heroes drew maps of continents and oceans, and eventually aimed our most powerful eyes toward the heavens to map the galaxies. In doing so, we painted a portrait of our universe as a vast dark canvas sprinkled with brilliant solitary islands of light. We saw clusters of galaxies pulled together by gravity, and we saw lone wanderers adrift in the unimaginable emptiness. The story we told ourselves was one of grandeur, yes, but also one of profound randomness of a cosmos born in a chaotic explosion and left to the haphazard pull of gravity. It is a beautiful story, a story of cosmic dustbins and accidental brilliance, and from our tiny vantage point it has always appeared to be true. But what if it's not? What if the chaos is a grand illusion, a magnificent sleight of hand performed on a scale so large our minds can barely comprehend it? What if the true story of the universe is not written in the dazzling light of the galaxies, but in the colossal echoing darkness that separates them? Imagine you are adrift in this cosmic ocean. The journey begins as a familiar one, pulling away from the soft blue marble of Earth, a world teeming with patterns with life. You accelerate past the familiar constellations, their ancient shapes dissolving into a meaningless jumble of stars as you breach the confines of our own Milky Way. Suddenly you are in intergalactic space, and the silence is absolute. The emptiness is staggering. Before you, a tapestry of unimaginable scale unfolds. You see Andromeda, a majestic spiral twin to our own hanging in the void. Further on the Triangulum galaxy, a smaller, scrappier companion. For millions of years of travel, you see little else. Just these isolated cities of light separated by gulfs of nothingness so profound they defy all terrestrial comparison. This is the universe as we have always pictured it, a collection of lonely islands in an endless dark sea. It is a universe of magnificent isolation. As we push further 1 billion light-years from home, the view changes. Galaxies are no longer individuals, but members of great swarms. You witness the Coma Cluster, a seething gravitational metropolis of over 1,000 galaxies, all churning and colliding in a frantic ancient dance. It feels like the heart of the cosmos, a place of immense density and power. Yet when you look beyond it, the emptiness returns even more stark and imposing than before. This flickering between dense clusters and profound emptiness reinforces the old story, the narrative of a universe that is clumpy, chaotic, and fundamentally unpredictable. But something is wrong with this picture. For decades, astronomers have been haunted by whispers of a deeper truth, by subtle clues hiding in the noise. When they began the monumental task of not just photographing galaxies, but meticulously measuring their distances, their positions in three-dimensional space, a ghost began to emerge from the data. The first crude maps looked like children's drawings connecting the dots of galaxies across billions of light-years. And what they revealed was not random. There were strange lines, impossibly long chains of galaxies stretching across the sky. There were vast, flattened sheets of galaxies that looked like cosmic walls. And most unnervingly, there were voids, immense spherical bubbles of near-perfect nothingness regions hundreds of millions of light-years across, where almost no galaxies existed at all. The universe, it seemed, was not a random scattering of points. It had a texture, it had a grain. It was as if we had spent our entire existence looking at the shimmering surface of the ocean, mesmerized by the individual waves without ever realizing that beneath it all lay a hidden landscape of mountains, canyons, and continental shelves, dictating the flow of every current. This hidden landscape, this fundamental architecture of reality, is what scientists now call the cosmic web. It is the most massive and most elusive structure in existence, and it turns our old picture of the cosmos completely inside out. The galaxies, the dazzling stars, the nebulae, all the things we can see, all the matter we have ever known are not the main event. They are merely the foam on the waves, the luminous debris caught in a current far greater than themselves. They are the decorations hung upon an invisible scaffolding that permeates all of space. This scaffolding is woven from the one substance that dominates our universe, yet remains almost entirely beyond our senses: dark matter. It is the great unknown, an ethereal, transparent material that does not burn, does not shine, does not reflect light. It is a cosmic ghost passing through our planet, through our bodies, through the very heart of stars without leaving so much as a whisper. And yet its presence is undeniable. Its gravity is the cosmic glue that holds our galaxies together, preventing them from flying apart as they spin. Without it, the universe as we know it simply could not exist. It is this invisible substance that forms the skeleton of the cosmos. Imagine the moments just after the Big Bang. The universe was an almost perfectly smooth, hot, dense soup of matter, dark matter, and energy. But there were minuscule fluctuations, tiny regions that were infinitesimally denser than others. Over eons, the relentless pull of gravity began to work on these imperfections. The dark matter, being 5 times more plentiful than normal matter, was the true architect. It began to collapse first, its gravity forming a vast interconnected network of structures. It didn't clump into spheres, but was pulled by the gravity of its neighbours into long, sinuous threads and massive dense knots where those threads intersected. It became a universal loom weaving a 3-dimensional tapestry that would span the observable universe. The normal matter we are made of the gas and dust that would one day form stars and planets, and people was just along for the ride. It was a secondary ingredient pulled by the irresistible gravity of the dark matter scaffold. It flowed through the cosmos like rainwater carving channels in a landscape draining into the deepest gravitational valleys already carved out by the invisible dark matter. This process created the distinct awe-inspiring components of the cosmic web. The grandest are the filaments. These are the great rivers of the cosmos, colossal bridges of dark matter and gas stretching for hundreds of millions of light years connecting the great galactic clusters. They are the cosmic highways channeling matter and entire galaxies from the emptier regions of space towards the great intersections. Along these filaments, galaxies are born like beads on a string, their formation sparked by the dense rivers of gas flowing through these invisible tendrils. If you could see them, they would crisscross the universe like a luminous, shimmering nervous system, a network of unimaginable scale and complexity, pulsing with the flow of creation itself. Where these mighty filaments intersect, you find the second component, the nodes. These are the great crossroads of the universe, the points of highest density where the cosmic highways converge. Here, the gravitational pull is overwhelming. These nodes are the birthplaces of the most massive structures we can observe, the superclusters of galaxies. They are the bustling, chaotic, dazzling metropolises of the cosmos, teeming with thousands of galaxies all caught in a gravitational storm merging, colliding and tearing each other apart in a spectacular display of cosmic violence and creation that has raged for billions of years. They are the universe's great centres of commerce and industry, where the raw materials flowing down the filaments are forged into new generations of stars. And then there are the voids. Between the shimmering filaments and the blazing nodes lie the great deserts of the cosmos. These are the most mysterious and perhaps the most profound components of the web. Immense, nearly empty, spherical regions that have been drained of their substance, their matter siphoned away by the gravity of the surrounding filaments and nodes. They are oceans of near-perfect nothingness so vast that our entire Milky Way galaxy could cross one and barely notice the journey. For billions of years they have been expanding, pushing the filaments and nodes further apart, driven by the mysterious force of dark energy. To journey through a void would be the loneliest experience imaginable. For 100 million years of travel you would see almost nothing. The bright cities of the superclusters would fade into faint distant smudges and the sky would grow darker and emptier than anywhere else in the universe. In their silent, desolate beauty, the voids represent the ultimate fate of our cosmos, a glimpse into a future where the relentless expansion of space will have stretched the cosmic web so thin that its luminous threads finally snap, leaving every galaxy cluster isolated in its own private, unreachable universe. Filaments, nodes, and voids. This is the true anatomy of the universe. Not a random spray of celestial shrapnel, but an intricate, organized, and deeply interconnected biological system. It is a single gargantuan structure, and we are living inside of it. For all our scientific progress, this colossal truth has remained just beyond our grasp, a theoretical framework supported by tantalizing but incomplete evidence. We could see the effects of the web, the alignment of galaxies, the gravitational lensing of distant light, the shadows cast by its gas on faraway quasars, but we could not see the web itself. Mapping a structure that is 95% invisible has been the single greatest challenge in modern cosmology. It is an act of charting a ghost. How do you draw the boundaries of a continent made of transparent matter? How do you trace the path of a river that emits no light? It required a complete rethinking of what a map of the universe could even be. It demanded new instruments, new techniques, and a new kind of creative scientific detective work capable of piecing together clues from a dozen different sources. It meant looking not for the light of the web itself, but for the subtle ways it imprints itself upon the light that passes through it, like finding the shape of a window by observing the distortion of the landscape seen through its glass. This quest has pushed our technology and our ingenuity to their absolute limits. It has been a multi-generational effort involving thousands of scientists and the most sophisticated telescopes ever built by humankind. And now, for the first time in the history of our species, that quest is bearing fruit. We are standing at the dawn of a new era of cosmic cartography. This is the story of that revolution. It is the story of how we are finally pulling back the curtain of darkness and revealing the universe's true skeleton. Combining the precise locations of millions of galaxies with the faint spectral fingerprints of intergalactic gas and the subtle gravitational warping of spacetime itself, scientists are piecing together the first comprehensive three-dimensional map of the cosmic web. This is not an artist's impression. It is not a computer simulation. It is a genuine chart built from real observational data, a testament to our relentless curiosity. We are moving beyond the two-dimensional photograph of the night sky and entering into a fully realized immersive understanding of cosmic geography. We are at long last learning the layout of our own universal home, tracing its highways, identifying its capital cities, and plumbing the depths of its great desolate oceans. This map is more than just a picture. It is a Rosetta Stone for the cosmos. Within its intricate patterns lie the answers to some of the deepest questions we have ever dared to ask. By tracing the flow of matter along its filaments, we can finally witness galaxy formation, not as a theoretical model, but as a live unfolding process. By measuring the precise shape and growth of the voids, we can probe the very nature of the dark energy that is accelerating the expansion of our universe, the force that will ultimately decide its fate. The map reveals the primordial blueprint laid down in the first moments after the Big Bang, allowing us to test our most fundamental theories of creation. It is a tool for cosmic archaeology, for cosmic engineering, and for cosmic prophecy all in one. It gives us context. It shows us our place. It reveals that our Milky Way is not a solitary island, but a small settlement on the outskirts of a vast filament, flowing inexorably toward the Great Virgo Cluster, a bustling node in our local corner of the web. This cosmic map reveals that we are part of something so much larger, so much more structured, and so much more interconnected than we ever dreamed possible. Our journey to understand the universe has reached a profound turning point. The age of seeing only the brilliant lights in the darkness is over. The age of charting the darkness itself has just begun. What if the most important thing in the universe is the nothingness? Not the brilliant burning stars or the majestic spiral galaxies, but the vast silent and seemingly empty chasms that separate them. For generations we looked out into the cosmos and saw points of light scattered across a black velvet backdrop like jewels spilled by chance. The universe on its grandest scales was thought to be uniform, a homogeneous sea of matter, abiding by a principle of cosmic modesty. It suggested that our place, our galaxy, our neighbourhood, was in no way special. This was the comfortable, orderly cosmos we believed we inhabited, a universe whose beauty lay in its simplicity, its predictable grandeur. But this elegant picture, like so many in the history of science, was destined to be torn apart by the relentless pull of evidence. The first hints of a deeper, stranger architecture came not from a grand revelation, but from the patient, almost stubborn act of counting. In the 1930s, the brilliant and notoriously cantankerous astronomer Fritz Zwicky turned his telescope towards the Coma Cluster, a dense swarm of galaxies. He saw something that should have been impossible. The galaxies within the cluster were moving, spinning around a common centre, at speeds so fantastically high that the gravity of all the visible stars could never hope to contain them. By all rights, the cluster should have flown apart, its members flung into the void. Zwicky realised there had to be something else there, a hidden source of gravity. Something unseen, unfelt and profoundly massive holding this cosmic city together. He called it dunkle materie, dark matter. It was an idea so far ahead of its time that for decades it was dismissed a footnote in the cosmic story, the eccentric theory of a difficult man. Yet this was the first clue that the universe's true nature was hidden from our eyes, that the light we saw was only a fraction of the story, a faint glimmer in an overwhelmingly dark reality. The gravity was real, and it was whispering of a hidden kingdom. Decades later, another rebellion against cosmic uniformity began to stir. The French-American astronomer Gérard de Vaucouleurs looked closer to home. He painstakingly plotted the positions of nearby galaxies, including our own Milky Way, and saw not a random scattering but a distinct pattern. He argued that we were living in a vast flattened structure, a pancake of galaxies he called the local supercluster. This was heresy. It violated the cherished cosmological principle. It implied that the universe did have structures, that it wasn't the same everywhere. It suggested that we lived on a great cosmic highway, not in a quiet cosmic suburb. Like Zwicky, he was met with skepticism. The universe, most believed, could not be this lumpy, this organised, this intricate. The cosmos was supposed to be grandly, simply uniform. But the evidence, quiet and persistent, kept accumulating. The real revolution began when astronomers stopped just taking pictures and started measuring the third dimension depth. By analysing the light from a galaxy, we can measure its redshift, the degree to which its light has been stretched by the expansion of the universe. This redshift is a direct measure of its distance from us. Suddenly we could build a three-dimensional map. We could finally see if these clusters and superclusters were real structures or just illusions, chance alignments on the two-dimensional dome of the sky. In the late 1970s and 1980s, a team at the Harvard-Smithsonian Center for Astrophysics, led by Margaret Geller and John Huchra, embarked on a monumental task. They began to systematically map a slice of the universe galaxy by galaxy redshift by redshift. It was grueling work, pointing a telescope at a faint smudge of light, gathering its photons for hours, decoding its distance, and then moving to the next. One point of light at a time, they were building a new cosmos. As the data points populated their plots, a picture began to emerge, one so astonishing that it would change cosmology forever. The galaxies were not scattered randomly like dust. They weren't even just in clumps. They formed immense interconnected chains and sheets, stretching for hundreds of millions of light years. These filaments of galaxies surrounded vast, shockingly empty regions, great bubbles of nothingness that came to be known as cosmic voids. In one of their most famous plots, they discovered a structure so clear, so undeniable, that it was nicknamed the Great Wall, an immense sheet of galaxies spanning more than 500 million light-years of space. This was no illusion. This was real. The universe was not a homogeneous soup. It was a sponge, a web, a skeleton. The comfortable, simple cosmos was gone, replaced by one of magnificent, bewildering complexity. The question was no longer if this structure existed, but how it could possibly have formed. The visible matter, all the stars and gas and dust we could see, was simply not enough. The gravity it generated was too feeble, too slow. In the 13.8 billion years since the Big Bang, there hadn't been enough time for such colossal structures to assemble on their own. It would be like trying to build a skyscraper in a single afternoon using only children's building blocks. Something was missing from our equations, a secret ingredient, a gravitational catalyst. And in that moment of crisis, Fritz Zwicky's ghost began to smile. His forgotten idea, dunkle materie, was about to take centre stage. Theorists turned from their telescopes to a new kind of observatory, the supercomputer. They began to construct virtual universes, digital boxes filled with particles governed only by the known laws of physics. They were attempting to grow a cosmos from scratch. To do this, they needed to know the recipe, the initial ingredients at the dawn of time, and for that we have a photograph. The cosmic microwave background, the faint afterglow of the Big Bang, is the baby picture of our universe. It shows us a cosmos just 380,000 years old, a hot, dense, and almost perfectly uniform fog. Almost perfect. Imprinted on this ancient light are minuscule temperature fluctuations, tiny ripples of destiny variations in density of less than 1 part in 100,000. These are the seeds. These faint smudges born from quantum jitters in the first moments of creation are the most important features in the entire universe. They represent the regions that were infinitesimally denser than their surroundings. And in the cosmos, gravity is the ultimate amplifier. The rich get richer. The slightly denser regions had slightly more gravity pulling in matter from their surroundings, growing ever denser, and in turn exerting an even stronger gravitational pull. It's an inexorable runaway process that continues to this day. But even with these seed simulations using only normal matter failed. The structures they produced were too small, too wispy, formed too late. The virtual universes looked nothing like the Great Wall revealed by Geller and Huchra. The answer the theorists realized had been hiding in plain sight for 50 years. They added Zwicky's dark matter to their simulations, but with a crucial new property. It had to be cold. Not cold in temperature, but in motion. It had to be slow, sluggish and heavy, not zipping around at near light speed. This cold dark matter would act as a cosmic anchor. Because it doesn't interact with light or radiation, it was free to begin clumping together long before normal matter could starting its work in the dim early ages of the universe. It formed vast invisible gravitational wells, a hidden scaffolding stretching across the cosmos. When the universe cooled enough for normal matter to be released from the grip of radiation, it found itself falling into a pre-existing architecture. It was like pouring iron filings over a table with magnets hidden underneath. The visible matter simply traced the invisible patterns that were already there. The scientists ran the simulations again. They programmed a digital box with the initial seeds from the cosmic microwave background, added the inexorable laws of gravity, and crucially included this invisible, gravitational architect cold dark matter. Then they pressed run and watched a universe be born. What emerged on their screens was a revelation. As cosmic time ticked by, the tiny density fluctuations grew amplified by the dark matter's gravity. The particles didn't just form isolated clumps. They were pulled into long, delicate filaments. They were flattened into immense flowing sheets. Where these filaments and sheets intersected, they formed dense, bright nodes, the cosmic equivalent of major cities. And between them, all vast regions were evacuated of matter, becoming the great cosmic voids. The simulation, born from pure mathematics and fundamental physics, had spontaneously, almost magically woven a web. It looked exactly like the universe the observers were mapping. The Great Wall, the filaments, the voids, they were all there. It was one of the most profound moments in the history of science, a convergence of two completely different paths of inquiry, the painstaking observational mapping of galaxies in the sky, and the purely theoretical simulation of a universe in a machine arriving at the very same extraordinary conclusion. The universe is built upon an invisible skeleton of dark matter. This is the cosmic web. This discovery solved the central mystery of the patchy, clumpy universe. The galaxies we see are not the web itself. They are merely the light strung along its frame. They are the luminous froth on a deep, dark, invisible ocean. They can only form in the very densest regions, the great nodes and filaments, where enough gas could accumulate to collapse and ignite into stars. The voids appear empty to us not because there is truly nothing there, but because the density of dark matter is too low for galaxies to ever be born. We are seeing only the brightest beacons on an unimaginably vast and intricate structure. Our view of the cosmos has been like looking at a country at night from orbit. We see the clusters of lights that are the cities, and we infer the roads connecting them, but we don't see the underlying landscape itself. But this grand synthesis also presented us with a monumental challenge, a puzzle, that would define the next generation of astronomy. The theory was beautiful, the simulations compelling, the indirect evidence overwhelming. But it was all predicated on a substance that accounts for over 80% of all matter, yet remains completely stubbornly invisible. We had created a blueprint for the universe's skeleton, but we had never seen the bones. How do you map a ghost? How do you prove definitively that these gossamer threads of dark matter truly stretch across the voids connecting the cities of light? How do you transform a theoretical model into a tangible three-dimensional map of the universe's true hidden structure? The quest was on not just to believe in the cosmic web, but to see it. And so the grandest structure in existence presented us with a profound paradox. A skeleton of unimaginable scale, holding together everything we have ever known, was itself almost entirely invisible. The cosmic web, this theoretical triumph born from simulations, demanded to be seen to be mapped, to be proven not just as an elegant idea, but as a physical reality shaping the heavens. But how do you chart a ghost? How do you survey an architecture built from darkness and whispers of hydrogen spread across billions of light years of chilling emptiness? The challenge was not merely technical, it was a fundamental confrontation with the transparent nature of our own universe. We were celestial cartographers tasked with drawing a continent shrouded in an impenetrable fog, knowing its mountains and valleys only by the way gravity pulled on distant ships. Our first most rudimentary tool was light itself, not the faint, almost non-existent glow of the web's own substance, but the brilliant beacons of the galaxies caught within it. If the web was the skeleton, then galaxies were the shimmering jewels embedded in the bone. By mapping their positions, we hoped to infer the shape of the unseen structure they inhabited. This was the dawn of the Great Redshift Survey's monumental undertakings of patience and precision that spanned decades. Astronomers began the painstaking process of pointing powerful telescopes night after agonizing night at one galaxy, then another, then 100,000 more. For each one, they captured its light and broke it apart into a spectrum, a rainbow barcode carrying a secret message. The message was hidden in the stretching of that light, the Doppler shift caused by cosmic expansion. A galaxy's redshift told us its distance, giving us the crucial third dimension that transforms a flat photograph of the sky into a true cosmic map. The earliest of these maps, like the landmark CFA Redshift Survey in the 1980s, were astonishing revelations. They peeled back the celestial sphere for the first time, showing us a universe that was anything but uniform. It was stringy, bubbly. Galaxies weren't scattered like dust. They were clustered into immense chains and sheets surrounding vast, shockingly empty voids. It was the first observational hint of the web, a slice of the universe that looked uncannily like the computer simulations had predicted. We saw the Great Wall, a staggering superstructure of galaxies stretching over 500 million light-years. We saw the Great Attractor, an unseen concentration of mass pulling our own Milky Way and thousands of other galaxies towards a mysterious gravitational centre. These were the nodes, the bustling intersections of the cosmic highway lit up for all to see. We were finally seeing the brightest, densest parts of the cosmic skeleton. But this method, for all its power, was like trying to understand the full shape of a tree by observing only the apples hanging from its branches. The galaxies showed us where the web was densest, but they told us almost nothing about the long, dark connecting filaments, and even less about the sheer emptiness of the voids they encircled. The vast majority of the web's mass, the dark matter that formed its very foundation, remained utterly beyond the reach of these surveys, and the intergalactic gas, the precious baryonic matter from which stars and planets are made, was too cold, too sparse, too electrically neutral to emit any light of its own. It was a cosmic mist 1 trillion times less dense than the air you're breathing now, and completely transparent to our telescopes. Our maps were biased, showing only the glittering peaks of a colossal hidden mountain range. We had sketched the cities, but the sprawling network of roads connecting them remained a mystery. A more profound technique was needed, one that could sense not just the light of the universe, but its very substance. We needed a way to weigh the darkness itself. The answer came from Einstein. His theory of general relativity had predicted a strange and wonderful phenomenon, that the fabric of space-time is not a passive stage, but an active participant in the cosmic drama. Mass tells space-time how to curve, and the curvature of space-time tells matter how to move. Crucially, it also tells light how to travel. A massive object like a galaxy or a cluster of galaxies acts as a gravitational lens, bending the path of light from more distant objects that passes nearby. This effect can be dramatic, creating spectacular arcs, and multiple images of the same background galaxy, a cosmic funhouse mirror. But astronomers realized that the principle could be applied on a far grander, more subtle scale. Even a diffuse filament of invisible dark matter containing the mass of 1 trillion suns stretched out over millions of light years should possess enough gravitational pull to create a tiny, almost imperceptible distortion. This is the realm of weak gravitational lensing. Imagine looking at a distant wallpaper pattern through a pane of old, slightly warped glass. Each individual motif on the wallpaper might seem normal, but if you analyze thousands of them, you'll notice a subtle, coherent pattern of distortion caused by the imperfections in the glass. In this analogy, the distant wallpaper is the sea of background galaxies, billions of them scattered across the deepest reaches of space. The warped glass is the invisible cosmic web lying between us and them. Individually, galaxies have their own intrinsic shapes, spirals, ellipticals, irregulars, but on average, across a large enough patch of sky, their orientation should be completely random. If we observe a region where thousands of distant galaxies seem to be faintly aligned, their shapes stretched in a similar direction like iron filings around a magnet, we have found a gravitational anomaly. We have found an invisible concentration of mass. We have found a piece of the web. This was a Herculean task of data analysis. It required imaging vast swathes of the sky with incredible depth and clarity, cataloguing the precise shapes of hundreds of millions of faint, faraway galaxies. Sophisticated algorithms then had to search for the telltale statistical alignment, a signal so faint it could easily be mistaken for instrumental noise or atmospheric distortion. For years, the evidence was tantalizing but inconclusive. Then, with the advent of powerful wide-field cameras on telescopes in Chile and Hawaii, and the unwavering eye of the Hubble Space Telescope, the signal began to emerge from the noise. By mapping these subtle shears and stretches across the sky, astronomers began to build a new kind of map. Not a map of light, but a map of mass. A map of the universe's gravitational field. And there it was. Long, sinuous bridges of matter reaching across the voids, connecting the bright galaxy-rich clusters just as theory had predicted. It was the first direct visualization of the dark matter filaments. We were seeing the true skeleton, the unseen scaffolding upon which everything else was built. This gravitational mirage, this ghostly imprint on the fabric of space-time, confirmed that the web was real, its dark architecture as vast and as influential as we had imagined. It was a triumph, a moment where we had managed to see the unseeable, but it still left a crucial part of the puzzle in the dark. Weak lensing could show us the dark matter, the dominant ingredient, but it could not distinguish it from the diffuse gas, the normal matter that should be mixed within it. To complete our census of the cosmos, we had to find a way to detect that gas. The universe in its generosity had provided the perfect tool for the job. Scattered across the cosmos are quasars, the most luminous objects in existence. A quasar is not a star, but the furiously bright heart of a young galaxy, where a supermassive black hole is actively feeding on a torrent of gas and dust. As this material spirals into the black hole's maw, it is heated to millions of degrees, unleashing a torrent of radiation so intense it can outshine its entire host galaxy by 1,000 times. They are cosmic lighthouses blazing across billions of light years, their brilliant piercing beams travelling through the universe for eons before reaching our telescopes. And like a lighthouse beam cutting through fog, their light carries a record of everything it has passed through. This is the science of absorption spectroscopy. Imagine the quasar's light as a perfect pure white light containing all the colours of the rainbow. As this beam journeys through the vast emptiness between galaxies, it inevitably encounters the tenuous clouds of hydrogen and helium gas drifting within the filaments of the cosmic web. While this gas is too faint to emit light, it is not completely inert. The atoms within these clouds are hungry for energy. An electron in a hydrogen atom can absorb a photon of light, but only if that photon has a very specific energy, a precise wavelength corresponding to the jump between the atom's energy levels. For hydrogen, the most prominent of these absorptions occurs in the ultraviolet part of the spectrum. It's called the Lyman alpha transition. So as the quasar's smooth, continuous spectrum of light passes through a cosmic gas cloud, the hydrogen atoms within it pluck out photons at that exact Lyman alpha wavelength. When the light finally arrives at Earth, billions of years later, Its spectrum is no longer smooth. It is riddled with dark, narrow lines like gaps in a barcode. Each line is a shadow, a spectral fingerprint left by a cloud of gas somewhere along the line of sight. And here is where it becomes truly powerful. Because of the expansion of the universe, each of these intervening clouds has a different redshift. A cloud closer to us will absorb light at a wavelength that is only slightly shifted towards the red. A cloud much farther away near the quasar itself will absorb a light that is then stretched over a much longer journey, so its absorption line appears at a much redder wavelength on our spectrum. The result is not a single absorption line, but a dense collection of hundreds of them, each at a slightly different position, each corresponding to a different clump of gas at a different distance. This thicket of spectral lines is known as the Lyman alpha forest. It is an astonishingly detailed one-dimensional core sample of the universe. By analysing the Lyman alpha forest in the light of thousands of different quasars, we could finally begin to probe the cool, diffuse gas that makes up the filaments. We could measure its density, its temperature, its chemical composition. We were no longer blind to the most common form of normal matter in the cosmos. The quasars were acting as celestial X-rays, and the web's gassy tendrils were showing up as shadows on the film. We had found the missing baryonic component of the great cosmic filaments. We had weighed the dark matter with lensing, and we had detected the gas with quasar light. The picture of the cosmic web seemed at last to be falling into place. But as our observations grew more precise, a deeply unsettling problem emerged from the data. A cosmic accounting error of staggering proportions. The science of the Big Bang is remarkably precise. By studying the faint afterglow of creation, the cosmic microwave background, we can calculate with incredible accuracy the total amount of normal baryonic matter that should exist in the universe today. This cosmic budget is a cornerstone of modern cosmology. So astronomers set out to conduct a census to add up all the normal matter we could actually see. They counted the stars in all the galaxies. They measured the vast clouds of gas and dust within those galaxies. They tallied the scorching hot plasma found in the great galaxy clusters. And using the Lyman alpha forest, they estimated the mass of the cool, diffuse gas in the filaments. They added it all up again and again with ever-improving data, and the numbers never matched. The sum of everything we could find, every star, every nebula, every filamentary cloud came up desperately short. It wasn't a small discrepancy. It was a chasm. Roughly half of all the normal matter that must exist according to our best cosmological theories was simply gone. Vanished without a trace. We knew the dark matter was there, its gravitational influence was undeniable. But this was different. This was the stuff we are made of. Protons, neutrons, electrons. The very elements forged in the heart of the Big Bang. And we had lost half of it. It wasn't in galaxies, it wasn't in clusters, and according to our Lyman alpha measurements, it wasn't in the cool, tenuous gas that made up the filaments we could probe. This was the dawn of the missing baryon problem. It was a crisis that struck at the heart of our understanding of cosmic structure. Had we profoundly misunderstood the nature of the cosmic web, or was there some other component to this grand architecture, a state of matter hidden in plain sight lurking in a thermal shadow zone, where it was too hot to be seen by our quasar probes, yet too diffuse to be detected by our X-ray telescopes? The universe's skeleton was proving to be more complex and more mysterious than we ever imagined. Finding this missing matter would become one of the next great quests in astronomy, a search that would force us to develop entirely new ways of seeing the universe, and to confront the violent, turbulent processes that shape the web's fiery intersections. For decades, the Great Web remained a ghost in the machine, a sublime silent prophecy whispered by the cold logic of supercomputers, yet stubbornly invisible to our most powerful eyes. The simulation screamed its existence, painting ghostly architectures of matter across virtual universes. But when we turned our telescopes to the heavens, we saw only the islands of light, the galaxies scattered like luminous dust against an incomprehensible void. The filaments, the great rivers of creation connecting everything, were missing. The cosmic skeleton that gave the universe its very shape was an article of faith, not a fact of observation. A profound and frustrating disconnect lingered between the universe we knew existed and the one we could actually prove. We were cartographers with a beautiful theoretical map of a new world, but we were blind. The stalemate could not hold. Humanity's insatiable curiosity, its relentless drive to turn shadow into substance, was building towards a critical mass. The turning point wouldn't come from a single shattering discovery, but from a powerful confluence, a perfect storm of technological innovation and computational might that together would finally give us the eyes to see the invisible. It began as great leaps often do with a change in philosophy. For a century, astronomy had been an act of targeted looking, of pointing our greatest instruments at a single fascinating object, a distant galaxy, a dying star, a stellar nursery. We were collecting exquisite portraits. But to map a ghost, you don't need a portrait. You need a dragnet. You need to survey the entire ocean. A new generation of telescopes was being forged for precisely this purpose. These were not the needle-sharp instruments of old, but wide-eyed behemoths designed to gulp down the sky in enormous sweeping drafts. Atop a remote mountain in New Mexico, the Sloan Digital Sky Survey began its methodical work not as a telescope in the classical sense, but as a celestial census taker. Night after patient night, its eye scanned the dark, systematically capturing the position and properties of millions upon millions of galaxies. It was a brute force approach to cosmology, an attempt to overwhelm the mystery with sheer unadulterated data. Each galaxy captured was another pinprick of light, another potential node in the unseen web. But a two-dimensional map, no matter how detailed, is just a photograph. It lacks depth perspective, the crucial third dimension that would transform a flat projection into a true cosmic architecture. The key, the secret to unlocking that third dimension, lay hidden in the light itself. It required a different kind of instrument working in perfect concert with the wide-field images. The spectrograph, the humble prism's technological descendant, became the master tool of this new cartography. Where a camera captures a galaxy's image, a spectrograph dissects its light, splitting it into a rainbow of constituent frequencies, a unique barcode of its chemical makeup temperature, and most importantly, its motion. As the universe expands, it stretches the very fabric of space-time, and any light travelling through that fabric is stretched along with it. Light from a galaxy moving away from us is shifted towards the red end of the spectrum, a phenomenon we call redshift. The greater the distance, the faster the galaxy recedes, and the more extreme its redshift. This was the cosmic yardstick. By precisely measuring the redshift for every single galaxy in the survey, we could calculate its distance from us with breathtaking accuracy. Suddenly, the flat tapestry of the sky began to peel apart, revealing its staggering depth. What looked like close neighbours on a photographic plate were revealed to be separated by hundreds of millions of light years, one far in the cosmic background, the other relatively close. The Sloan survey and others like it became robotic redshift factories. Optical fibres plugged into massive plates by hand in the early days, and later by sophisticated robots, would drink in the light from 1,000 galaxies at once, feeding their stellar songs into the waiting spectrographs. Night after night the data poured in. 1,000 galaxies became 100,000. 100,000 became 1,000,000. We were no longer just looking at the universe. We were mapping it point by painstaking point, building a three-dimensional model of our cosmic neighbourhood on a scale that defied imagination. This colossal undertaking created a problem of its own, a challenge not of physics, but of pure information. The torrent of data flowing from these new surveys was unlike anything humanity had ever dealt with before. It was a digital avalanche, a tsunami of petabytes that would have drowned the computing systems of the previous generation. Each galaxy was a string of numbers, its coordinates on the sky, its brightness, its size, and its crucial redshift value. To find the delicate gossamer structure of the cosmic web within this blizzard of data was like trying to discern the shape of a forest by examining 1 billion individual leaves. The human mind alone could not perceive the pattern. We needed a new kind of partner in discovery. That partner was the algorithm. Deep within the humming server farms of universities and research institutes, new computational techniques were being born. Programmers and astrophysicists worked side by side, crafting elegant pieces of code designed to act as digital prospectors to sift through the mountains of raw data and pan for the gold of cosmic structure. These algorithms were trained on the virtual universes of our simulations. They learned to recognize the mathematical signatures of clusters, the dense gravitationally bound cities of the cosmos. They learned to identify the vast empty deserts we call voids. And most critically, they learned how to trace the faint thread-like connections between the clusters, the telltale alignments of galaxies that betrayed the presence of an underlying filament. The moment of revelation did not happen with a shout in a laboratory, but with the quiet hum of a processing core. As the algorithms churned through the real-world data from the sky, the structure began to emerge, resolving itself from the noise. It was hesitant at first, like a developing photograph, a ghostly impression taking shape. But as more data was added as the map expanded from a few million galaxies to hundreds of millions, the image sharpened into irrefutable clarity. There it was. Not a ghost, not a theory, but a magnificent, undeniable reality. Before our eyes on monitors displaying the processed data, the universe's skeleton was laid bare for the first time. We could see it, the great chains of galaxies stretching for 500 million light-years forming the luminous seams of the cosmic tapestry. We could see the superclusters, the grand intersections where filaments converged blazing with the light of thousands of galaxies. And we could see the voids, the deep dark and achingly empty spaces in between, whose very emptiness served to define the brilliant structures around them. It was a map unlike any other in human history. We could fly through it. Using the 3D coordinates of every galaxy, we could navigate this celestial architecture soaring down the length of a filament, banking around a colossal cluster, and plunging into the silent depths of a void. We were no longer confined to the surface of our sky. For the first time, we were truly exploring the cosmos in 3 dimensions. The simulations had been right. The elegant mathematics that predicted this structure had been vindicated in the most spectacular way imaginable. We had found the scaffolding of the universe. Yet even in this moment of triumph, a deeper mystery remained, a question that was now more urgent than ever. We had mapped the lights on the highway, but where was the highway itself? The galaxies we understood were merely the froth on a much deeper, unseen river of matter. The vast majority of the web's material, over 80% of the ordinary baryonic matter within it, was not locked up in shining stars and galaxies. It existed as an impossibly thin, searingly hot gas, a diffuse plasma of hydrogen and helium stretching between the galaxies known as the intergalactic medium. This was the true substance of the filaments. The galaxies were just the luminous beacons, the cosmic "you are here" signs that allowed us to trace the underlying structure. Finding this gas was the final formidable challenge. It was like trying to see the air between 2 distant streetlights on a foggy night. This gas doesn't shine on its own, and it is so incredibly tenuous in some places, just a few atoms per cubic meter, that it is effectively transparent. It was the universe's ultimate ghost, and catching it would require a technique of almost supernatural subtlety. The solution came not from looking at the empty space, but from looking through it. The key was to find a perfect source of background illumination, a celestial lighthouse so immensely powerful that its beam could travel across billions of light-years unchanged and pure. Nature fortunately had provided just such a beacon, the quasar. A quasar is the hyperactive heart of a young galaxy, where a supermassive black hole is feeding on a torrent of gas and dust. This cosmic feeding frenzy unleashes a flood of radiation so cataclysmically bright that it can outshine its entire host galaxy by a factor of thousands. A single quasar located on the far side of the universe can appear brighter to our instruments than a nearby star. They are the perfect cosmic searchlights. The idea was exquisitely simple in its conception, yet fiendishly difficult in its execution. You find a distant quasar whose line of sight by sheer cosmic chance passes directly through one of the newly mapped galaxy filaments. You then take a meticulous high-resolution spectrum of that quasar's light. For most of its journey, the light travels through the near-perfect vacuum of the cosmic voids, but when it intersects the filament, it must pass through that thin, invisible fog of hydrogen and helium gas. While the gas is too sparse to block the light, the individual atoms within it are not completely passive. An atom of hydrogen, the most abundant element, is tuned to absorb photons of very specific energies, very specific frequencies of light. When a photon with exactly the right energy hits a hydrogen atom, it is absorbed, kicking the atom's electron into a higher energy state. The effect on the quasar's light is subtle but profound. From the pure, continuous rainbow of the quasar's spectrum, a tiny sliver of light is missing. It has been absorbed by the gas in the filament. This creates a dark, narrow line in the spectrum, an absorption line. It is a shadow, a whisper in the starlight, a chemical fingerprint of the invisible gas that the light passed through. Finding this shadow was the goal. Astronomers began a painstaking campaign using the world's largest telescopes to capture the spectra of hundreds of distant quasars whose light paths intersected the 3D map of the Webb. Each spectrum was a coded message from the void, a historical record of everything the light had encountered on its multi-billion-year odyssey to Earth. The data was a forest of spectral lines, a complex barcode of cosmic history. But using the redshift of the galaxies in the filament, scientists knew exactly where in the spectrum to look for the telltale absorption signature of hydrogen gas at that specific distance. And then they found it, time and time again. A quasar beam would pass through a region on the map where galaxies clustered in a filamentary line, and precisely at the corresponding redshift in its spectrum, the characteristic shadow of hydrogen absorption would appear. When the line of sight passed through a void, the shadow vanished. It was irrefutable. The correlation was perfect. This was not just a statistical anomaly, it was the direct, tangible detection of the cosmic web's primary substance. We had finally seen the ghost. We had proven that the empty spaces between the galaxies were not truly empty. They were filled with the very stuff from which galaxies are made the raw material for cosmic construction, flowing along the gravitational channels carved out by dark matter. The discovery was a watershed moment, a final triumphant confirmation of a half-century of theoretical work. The Webb was real. Its structure traced by the galaxies was now confirmed to be filled with the primordial gas that fuels them. We had moved beyond mere cartography, beyond simply mapping the points of light. We were now beginning to understand the cosmic ecology, to see the universe not as a static collection of objects, but as a living, breathing system. We had found the universe's circulatory system, the great arteries and veins that ferry matter and energy across the cosmos, feeding nascent galaxies and shaping the grand destiny of everything we see. The map was no longer just a map of where things are. It was becoming a map of how things work, opening a spectacular new chapter in our quest to understand our place within this vast, interconnected and luminous reality, undefined. And so the map is unrolled before us. Not a static chart of celestial locations, but a living blueprint pulsing with unseen energies, a neuro-architectural marvel of the cosmos itself. For the first time we can step back and see the skeleton of the universe, this filigreed lattice of matter, connecting the great galactic cities across chasms of nothingness. But seeing the structure is only the first step on a far more profound journey. Holding this three-dimensional map in our minds, we are immediately confronted with a new, deeper set of questions. Is this web merely a passive scaffold upon which creation has been built, a relic of the Big Bang's initial whispers, or is it something more? Is it an active dynamic system? A cosmic circulatory network that continues to shape and define the fate of every star, every planet, and every galaxy within it? The answer begins not in the brilliant glittering filaments, but in the desolate emptiness of the voids. For millennia we saw these as dead spaces, the forgotten backwaters of the universe. But our new perspective reveals them as immense cosmic reservoirs, the source of a slow, inexorable migration of matter. These are not static bubbles of nothing. They are expanding, powered by the mysterious engine of dark energy, and in doing so they act like colossal bellows squeezing the primordial gas that lingers within their boundaries. This gas, mostly hydrogen and helium left over from the dawn of time, is shepherded by the gentlest of gravitational gradients. It begins to flow almost imperceptibly at first, trickling out of the void and towards the nearest filament. You're witnessing the very headwaters of a gravitational river system that spans billions of light years. Imagine a vast continental watershed on Earth. Rain falls, gathers in streams which merge into rivers, all flowing downhill toward the sea. The cosmic web operates on an astonishingly similar principle. The voids are the high plateaus and the filaments are the river valleys. the gas flows from high density to higher density, a journey that takes hundreds of millions, even billions of years. As it travels, this material is not unchanged. It is compressed, heated, and begins to acquire a spin, a subtle angular momentum gifted to it by the tidal forces of the surrounding large-scale structures. This is no longer the pristine, simple gas of the early universe. It is being prepared pre-processed, seasoned for the crucible of creation that awaits it. We call this flowing material the intergalactic medium, but that name belies its true nature. It is the lifeblood of the cosmos, the raw fuel for all future stars, and it is flowing along these immense invisible highways. These highways, the filaments themselves, are not uniform pipelines. They are complex structures braided and knotted with their own internal currents and shock waves. Where multiple filaments converge, the density of gas and dark matter skyrockets, creating the grand nodes of the web, the bustling metropolitan centres, where thousands of galaxies are drawn together into colossal clusters. It is along these filaments that the magic truly happens. They are celestial nurseries on an unimaginable scale. Within these dense rivers of inflowing gas, gravity can finally overcome the outward pressure of the gas itself. Clouds begin to collapse under their own weight, fragmenting into smaller and smaller clumps. These clumps become protogalaxies, the seeds of the magnificent spirals and ellipticals we know today. We can see this process unfolding across cosmic time. By looking at distant filaments, we see light from billions of years ago, and there the galaxies are small, blue and chaotic, furiously birthing new stars from the rich supply of gas they are swimming through. They are like fledgling organisms feeding directly from the umbilical cord of the cosmic web. But as we look at filaments closer to us, and thus closer to the present day, the picture changes. The galaxies are larger, redder, more settled. They have exhausted much of their initial fuel supply. They have grown, matured, and their frantic star formation has slowed to a crawl. The web has nurtured them from infancy to adulthood. This confirms a revolutionary idea: a galaxy's evolution is not a solitary affair. Its entire life story, its size, its shape, its colour, its ultimate fate is fundamentally dictated by its address, by its precise location within this cosmic superstructure. It is a story of nature and nurture on the grandest possible scale. But the relationship is not one-sided. Galaxies do not just passively receive this cosmic bounty. They fight back. They regulate their own growth in a dramatic and violent feedback loop, and the agent of this regulation lies deep within their cores in the most extreme objects we know of: supermassive black holes. For decades we pictured these gravitational monsters as mere points of no return, cosmic drains, devouring everything that strayed too close. Now we understand they are cosmic engines, the beating hearts of their galactic hosts, profoundly influencing their environment. As the filament's gas stream pours into a young galaxy, it spirals toward the centre, forming a vast, brilliant accretion disk around the supermassive black hole. The friction and gravitational shear in this disk heat the material to millions of degrees, causing it to blaze with the light of a trillion suns. This is a quasar, a celestial blowtorch visible across the entire universe. The intense radiation blasting out from the quasar exerts an enormous pressure on the inflowing gas, capable of halting its descent, and in some cases pushing it back out of the galaxy altogether. But that is only one half of the story. The black hole doesn't just shine, it erupts. As the accretion disk becomes overloaded, magnetic field lines twist and snap, launching unfathomably powerful jets of particles away from the black hole's poles at nearly the speed of light. These jets are cosmic sandblasters. They tear through the galaxy, inflating huge bubbles in the interstellar medium, heating the gas to temperatures so high that it can no longer cool and collapse to form stars. This process, known as active galactic nucleus feedback, is the universe's primary self-regulation mechanism. The supermassive black hole acts as a galactic thermostat. When the flow of cold gas from the filament is too great, the black hole engine roars to life, heating or expelling the excess fuel and shutting down star formation. When the galaxy cools and gas begins to flow in again, the cycle can restart. This is a delicate, eons-long dance between the relentless pull of gravity drawing material in along the web and the violent push from the central black hole ejecting it back out. Without this feedback, our simulations show that galaxies would be monstrously large, bloated with stars and burning through their fuel far too quickly. The elegant spirals we see would not exist. The universe would be a far less structured, far less interesting place. The cosmic web provides the meal, but the black hole at the core decides how much the galaxy is allowed to eat. It is the ultimate gatekeeper of galactic growth. This intricate dance of inflow and feedback paints a picture of a universe in a state of dynamic equilibrium. But there is another force at play, a silent, pervasive presence that is slowly but surely changing the rules of the game. It is the ghost in the cosmic machine dark energy. This mysterious repulsive force, an intrinsic property of space itself, is the power source behind the accelerating expansion of the universe. While gravity works to pull matter together, building the magnificent structures of the web, dark energy works to push everything apart, and its influence is most profound where gravity is weakest in the great voids. Dark energy is causing the voids to swell to expand faster and faster, like balloons inflating in the cosmic dough. As they grow, they stretch the filaments that connect them. The great gravitational rivers are being elongated, their currents thinning out. The nodes, the great galactic clusters, are becoming more and more isolated as the empty spaces between them grow at an accelerating rate. We are witnessing a cosmic tug-of-war on the largest of all scales. On one side is gravity, the great architect tirelessly weaving the web and pulling matter into glorious congregations. On the other is dark energy, the great isolator relentlessly pulling the threads of the tapestry apart. At this moment in cosmic history, gravity is still winning on local scales. The filaments hold, the clusters remain bound. But the models are clear about the long-term forecast. As the eons pass, dark energy's influence will grow ever more dominant. The stretching will intensify. Filaments will eventually snap their supply lines of gas cut off. The flow from the voids will cease their reservoirs having been pushed too far away to ever reach the galactic shores. One by one, the great superclusters will become islands in an impossibly vast and darkening sea of emptiness. Each cluster will become its own isolated universe, unaware of the others, their light red-shifted into oblivion by the runaway expansion of the space between them. The cosmic web, this vibrant, interconnected structure that nurtured the birth of galaxies, will be dismantled. The universe is slowly pulling itself apart at the seams. This looming fate adds a layer of cosmic poignancy to our discoveries. Yet even as we contemplate this distant future, the web continues to reveal deeper, more subtle secrets about the present. Recent astonishingly precise observations have uncovered a hidden alignment, a cosmic choreography that links the larger scales to the smallest. Astronomers have found that the spin of entire galaxies is not random. Galaxies residing on a filament tend to spin in alignment with the axis of that filament, like celestial gyroscopes arranged along a string. This is a truly mind-bending discovery. The angular momentum of an object 100,000 light-years across appears to be directly influenced by a structure that is hundreds of millions of light-years long. How is this possible? The leading theory suggests that the alignment is imprinted at the moment of birth. The gas flowing along the filaments already possesses a gentle coherent spin, a kind of cosmic vorticity. As this gas collapses to form a proto-galaxy, that initial large-scale angular momentum is conserved cascading down to the scale of the galaxy itself. It's as if the gravitational river impresses its own rotational memory onto the stellar systems it creates. This implies a level of coherence and connection across the universe that we're only just beginning to appreciate. It suggests that the formation of everything is governed by a kind of cosmic weather, with prevailing currents and directional flows that guide the assembly of matter from the dawn of time. The web isn't just a physical structure, it's a dynamic template that encodes the fundamental motions of the galaxies it spawns. With every new layer of complexity, we uncover our old vision of the cosmos. A static collection of objects scattered through a passive void recedes further into history. What replaces it is a far more majestic and intricate picture. We now see a universe that is not a collection of things, but a single interconnected entity. A vast cosmic ecosystem where the voids act as lungs, the filaments as arteries, and the galaxies as cells, each with its own regulatory nucleus. It is a system where gas is recycled, where energy is exchanged, and where the life story of one galaxy is inextricably linked to the grand overarching structure in which it is embedded. The map has shown us not just where we are, but what we are part of. We are part of a living, breathing, evolving cosmic network, and yet for all that we have learned by studying its intricate dynamics, we are haunted by the deepest question of all. This structure, this skeleton of space-time is so fundamental, so exquisitely tuned to the creation of galaxies that it feels almost inevitable, almost designed. But where did it come from? How did these initial ghostly whispers in the aftermath of the Big Bang, these tiny quantum fluctuations in the primordial soup, manage to orchestrate a structure of such breathtaking scale and complexity? To answer that, we must push our gaze back further, still beyond the first stars and galaxies, into the opaque fog of the cosmic dark ages, to hunt for the embryonic seeds from which this entire magnificent web first grew. For generations it remained a ghost in the machine of cosmology, a theoretical necessity whispered into existence by the mathematics of gravity and the faint echoes of the Big Bang. We had seen its shadow in the cosmic microwave background, a faint blueprint for a structure of unimaginable scale. We had inferred its presence from the strange coordinated dances of galaxies which refused to wander aimlessly through the void. They clumped and clustered as if tethered by unseen forces hinting at a hidden architecture, a grand design woven into the fabric of space-time itself. But for all our simulations, for all our indirect evidence, the web itself remained elusive. It was a cosmic skeleton with no flesh, an invisible continent whose shores we could only guess at. The central agonizing question lingered. How do you map what you cannot see? How do you bring a ghost into the light? The answer would not come from a single mind or a lone observatory, but from a monumental, multi-generational human endeavour. It would require us to transform our telescopes from passive windows into the night, into relentless high-speed surveyors, charting the cosmos not one star at a time, but millions. This was the dawn of the Great Surveys, the largest and most ambitious cartography projects in the history of our species. It began in earnest with endeavours like the 2DFA Galaxy Redshift Survey in Australia, a heroic precursor that painstakingly measured the distances to over 200,000 galaxies, providing our first tantalising pencil-thin slices of the local universe. These early efforts were revolutionary, revealing for the first time the unmistakable patterns of filaments and voids, but they were like mapping a continent by surveying a single coastline. To see the whole, to grasp the true three-dimensional majesty of the web, we needed to go bigger. We needed a celestial doomsday book. That call was answered by the Sloan Digital Sky Survey, or SDSS. Operating from the high desert of New Mexico, its dedicated telescope began a systematic campaign not just to photograph the sky, but to dissect its light. Night after night, year after year, it stared into the deep, capturing the positions of millions of galaxies and crucially measuring their redshift, the subtle stretching of their light that reveals their distance and speed. This was a fundamentally different way of doing astronomy. It was industrial-scale cosmology. Instead of a single astronomer pointing a telescope at a chosen target, Sloan used a revolutionary technique involving precisely drilled aluminum plates. Each plate was a stencil of a specific patch of sky with holes drilled at the exact locations of known galaxies and quasars. Hundreds of optical fibres were then plugged into these holes, by hand, a painstaking process that turned the telescope into a multi-eyed insect capable of capturing the spectra of hundreds of objects simultaneously. Each spectrum was a galactic fingerprint, a barcode of light containing a wealth of information. And within that barcode was the key, the redshift, our ultimate measuring tape for cosmic distances. As the data flowed in, a picture began to emerge not on a photographic plate, but inside the humming servers of a global collaboration. Point by point, galaxy by galaxy, the void was being populated. What was once a two-dimensional tapestry of stars was being pulled and stretched into a third dimension of breathtaking depth. The flat portrait of the heavens was gaining perspective, its true cavernous structure slowly resolving from the digital noise. But even Sloan, for all its power, was just one chapter in this epic. To push deeper into the cosmic past and map the web with even greater fidelity, we needed a new generation of instruments. We needed machines built for the express purpose of untangling this cosmic nervous system. From the mountains of Arizona, the Dark Energy Spectroscopic Instrument, or DESI, came online. It represents the apex of this technology. Mounted on the historic Mayol telescope, DESI's robotic heart can position 5,000 fibre-optic eyes with micron-level precision in mere minutes. It is a spectroscopic behemoth, capable of measuring the redshifts of tens of thousands of galaxies in a single night. This is not just an incremental improvement, it is a quantum leap in our ability to survey the universe. While previous surveys gave us the counties and states of the cosmic map, DESI is drawing. The individual cities, towns, and connecting highways across cosmic epochs, reaching back billions of years into the youth of the universe. It is a time machine and a cartographer all in one. Similar efforts like the Euclid Space Telescope launched by the European Space Agency are taking this quest into orbit, escaping the blurring effects of Earth's atmosphere to capture exquisitely sharp images and spectra, providing an independent complementary view of this same grand structure. For decades we had lived with the simulations. We had watched these ghostly luminous webs assemble themselves inside supercomputers, governed by the simple, elegant laws of gravity, and our best guesses about the universe's secret ingredients. They were beautiful, compelling, and consistent with everything we thought we knew. But they were still just theory. They were a prediction. Now, with the data from these colossal surveys finally stitched together, we could perform the ultimate comparison. We could hold our theories up to the harsh, unforgiving light of reality. And so the moment of revelation arrives, the culmination of millions of hours of observation of countless careers dedicated to a single audacious goal. Before you now is not a simulation. It is not an artist's impression. This is it. The universe as it truly is. Imagine we're pulling back from our own Milky Way, travelling faster than light, the stars blurring into a stream. Soon, our entire local group of galaxies is just a small glittering knot. As we accelerate outwards, other knots appear linked by faint shimmering bridges of light. We're moving through a structure that defies terrestrial comparison. It is a luminous, sprawling network that fills all of space. These are the filaments of the cosmic web, the great rivers of creation. They are incandescent superhighways stretching for hundreds of millions of light years, their lanes paved not with asphalt but with billions of galaxies. Each point of light you see is an entire island universe, a home to hundreds of billions of stars, and yet here it is reduced to a single grain of sand in a celestial desert. Follow one of these filaments. Watch how it twists and braids with others, its density thickening as it flows towards a junction. These junctions are the great cities of the cosmos, the nodes of the web. Here, gravity has won its most spectacular victories. These are the galaxy clusters, immense congregations of thousands of galaxies, all trapped in a frantic gravitational dance around a common centre. They blaze with the light of their constituent stars and glow in the X-rays of their superheated gas, marking the universe's most massive and densely populated intersections. You can feel the scale of it, the sheer overwhelming emptiness that separates these structures. Between the glowing filaments lie the great voids, the cosmic quiet zones. These are vast, profound oceans of darkness, some spanning over 100 million light-years across. They are not entirely empty. A few lonely, forgotten galaxies drift through their cavernous depths. But for the most part, they are the regions where the universe's initial matter was spread too thin, areas that gravity abandoned in its relentless quest to build the glittering structures we see elsewhere. They are the silent counterpoint to the vibrant web, their emptiness just as crucial to the overall architecture as the filaments themselves. For the first time, we can fly through them. We can navigate this three-dimensional labyrinth. We can turn a corner around a supercluster, plunge into the heart of a void, and emerge on the other side a billion light-years from where we started. We have moved from being flatlanders stuck on a two-dimensional projection of the sky to true cosmic explorers equipped with a map that reveals the length, the breadth, and most importantly, the depth of our universe's skeleton. The ghost has finally materialized. And the moment it did, it began to speak. The first thing it told us was a profound and deeply satisfying confirmation. When we lay the real map, our map, alongside the maps generated by our supercomputer simulations, the resemblance is breathtaking. It is not just a passing similarity, it is a near-perfect match in its statistical properties. The sizes of the voids, the thickness of the filaments, the mass of the clusters, all of it was predicted with stunning accuracy by our reigning cosmological theory, the lambda-cold dark matter model. It was a watershed moment for cosmology, a resounding validation that our understanding of the universe's fundamental ingredients and governing laws is in large part correct. The simulations were not just digital daydreams, they were prophecy written in the language of physics. The ghostly architecture our computers had been building for decades was, it turns out, real. This map proves that the force of gravity acting on a primordial soup of dark matter and regular matter over 13.8 billion years is indeed the master architect of the cosmos. Yet like any great discovery, this map is not merely a confirmation of what we already knew, it is also a source of new and tantalizing puzzles. When we scrutinize its details, we find subtle asymmetries and anomalies that the standard models struggle to explain. We see structures like the Great Wall, a colossal filamentary system stretching over 1 billion light-years larger and more coherent than many simulations would predict. We observe cosmic flows, vast rivers of galaxies all moving in the same direction, at incredible speeds, as if being pulled by something immense just over the cosmic horizon. These are the map's whispers of a deeper physics hints that our current theories, while powerful, are not yet complete. This map is not an endpoint. It is a new baseline, a fantastically detailed reference against which we can test every new idea about the universe's origins and evolution. It has provided us with the crucial data points needed to refine our theories, to hunt for the cracks in our understanding, where the next great revolution in physics might be hiding. Perhaps the map's most profound revelation, however, is what it tells us about the universe we cannot see. Remember, the light we are mapping comes from galaxies which are made of ordinary familiar matter. But we know that this ordinary matter is just the tip of the cosmic iceberg, constituting a mere 5% of the universe's total mass and energy. The vast majority is dark matter and dark energy. This map of light is in reality a map of the shadows. The galaxies are not the structure itself. They are merely the luminous traces of the underlying invisible scaffolding of dark matter. Like foam on the crest of an ocean wave, the galaxies collect and shine in the regions where dark matter is most dense. The filaments of light you see are tracing incomprehensibly vast filaments of dark matter. The blazing clusters of galaxies sit at the bottom of deep invisible wells of dark matter's gravity. We are seeing for the first time the shape of the gravitational field that dominates the universe. We have illuminated the ghost skeleton. This provides us with an unprecedented tool to study the properties of dark matter itself. By analysing the precise shape and connectivity of the web, we can place the tightest constraints yet on what this mysterious substance can and cannot be. And then there is the final cosmic battle playing out across this map. The entire magnificent structure, this intricate web of matter and energy, is not static. It is caught in a titanic tug of war. On one side, there is gravity amplified by the immense reserves of dark matter, relentlessly pulling everything together, trying to build ever larger structures. On the other side is a mysterious repulsive force woven into space-time itself, dark energy. This is the force that is accelerating the expansion of the universe, a cosmic anti-gravity that is constantly working to pull the web apart. It stretches the filaments, deepens the voids, and pushes the great superclusters away from each other. Our map is not a fixed monument. It is a snapshot of this ongoing conflict. By comparing the structure of the nearby, more recent web to the structure of the web in the distant past, we can directly measure the history of this cosmic struggle. We can see how the influence of dark energy has grown over billions of years, transforming from a minor player in the early universe to the dominant force it is today. This 3D map has become our most powerful laboratory for probing the nature of the single, greatest mystery in all of science. We have come so far, from ancient astronomers charting constellations with the naked eye to a global civilization building robotic surveyors to map the cosmos in 3 dimensions. We set out to find the universe's hidden architecture to confirm a theoretical ghost, and we succeeded beyond our wildest dreams. We have laid it bare, the glowing filaments, the dense nodes, and the cavernous voids. We have charted the cosmic nervous system that connects everything. This is the grand stage upon which the entire history of the universe has unfolded. It is the cradle from which our own galaxy was born, the environment that shaped our cosmic destiny. We now hold the blueprint in our hands, but like the first explorers to unroll a map of a new world, our work has only just begun. The map does not give us all the answers. Instead, it presents us with a new, more profound set of questions. Now that we can see the full extent of our cosmic home, we must begin the real work of understanding it. Where do these cosmic highways lead, and what other secrets lie hidden waiting to be discovered within their luminous threads? To finally see it laid bare across the cosmos is to witness the universe's most profound secret. For generations we gazed into the night and saw a majestic but ultimately disconnected scattering of lights. We saw islands of brilliance separated by an incomprehensible abyss of darkness. Our telescopes grew stronger, our vision deeper, and the islands became island universes, galaxies by the billions. Yet the fundamental picture remained the same, a universe of isolated points adrift in an eternal lonely sea. This map, this ghost of gravity made visible, has shattered that illusion forever. We now know with a certainty that resonates in the core of our being that nothing is truly alone. The great superclusters, those glittering archipelagos of galaxies, are not islands at all. They are the luminous knots, the bustling metropolises in a single continuous and impossibly vast cosmic structure. The voids once dismissed as mere emptiness have been revealed as the serene dark heartlands of this grand architecture, shaping the flow of matter and destiny with their subtle, repulsive power. From the grandest scale imaginable, our universe is not a collection of things. It is a relationship between them. It is an intricate interwoven tapestry, a network of shimmering filaments and dense nodes, all sculpted from the faint quantum whispers of the Big Bang itself. To have rendered this invisible skeleton, to have traced its filaments across billions of light years, is more than a triumph of technology and perseverance. It is a fundamental recalibration of our place within existence. We have for the first time read the autobiography of the universe written in the language of gravity. This new cosmology, born from the painstaking process of connecting the cosmic dots, is a revolution in understanding. For decades, our supercomputer simulations predicted this web-like structure. They showed us how a nearly uniform primordial soup of matter seeded with tiny fluctuations could, under the relentless pull of gravity over 14 billion years, collapse into this filigreed pattern. Dark matter, the silent and unseen majority, formed the gravitational scaffolding first. Then ordinary matter, the stuff of stars and planets, and people, was drawn into this cosmic framework like iron filings aligning to an invisible magnetic field. Galaxies bloomed along these filaments like dew on a spider's web at dawn. These simulations were magnificent, elegant theories, but they remained just that, theories. They were our best, most educated guess at the grand design. But with this map, we have crossed the threshold from theory into truth. We now possess the ground truth, the observational reality against which all our models must be tested. We can see where the simulations were brilliantly prescient and where they fall short, revealing subtle new physics we have yet to grasp. The map shows us the precise thickness of the filaments, the exact geometry of the junctions where clusters form. It allows us to measure the sheer soul-crushing scale of the voids with unprecedented accuracy. These are not just details. They are the crucial parameters that dictate the story of cosmic evolution. By comparing this intricate real-world data to our virtual universes, we can fine-tune our understanding of the cosmos's most enigmatic components. We can better constrain the nature of dark matter, determining whether it is cold and slow-moving as predicted, or if it possesses some other more exotic property that leaves a telltale signature in the web's finest threads. We can trace the tendrils back in time, cross-referencing their structure with the faint afterglow of the Big Bang, to understand the initial conditions of the universe with staggering precision. This is not merely about confirming what we thought we knew. It is about uncovering the questions we didn't even know to ask. It has transformed our view of galaxies themselves, no longer seeing them as self-contained systems, but as open ecosystems continually fed by vast cold rivers of gas that flow along the cosmic web. These filaments are the umbilical cords of galaxy formation, funneling the raw material needed for starbirth from the intergalactic medium directly into the hearts of galactic disks. The map allows us to see this cosmic plumbing in action, to understand why some galaxies are vibrant and star-forming, while others, starved of this vital supply, have faded into red and silent retirement. The universe, it turns out, is a living, breathing, interconnected system, and for the first time we have the anatomical chart to study its physiology. And yet the ink on this first revolutionary map is barely dry. As monumental as it is, we know it represents only the brightest, most prominent superhighways of the cosmic network. We have charted the continents, but a world of finer detail of county roads and hidden pathways still awaits discovery. A new generation of celestial cartographers is already preparing their instruments, poised to embark on voyages that will make this incredible achievement seem like a quaint hand-drawn chart of an old world. Soon, the Vera C. Rubin Observatory in Chile will begin its legacy survey of space and time. For 10 years, its enormous mirror and the world's largest digital camera will scan the entire southern sky every few nights. This will not create a static map, but a dynamic one, a celestial movie. We will see the cosmic web not just as it is, but as it changes. We will watch as supernovae flare up within its filaments, acting as standard candles to measure distances with greater precision. We will track the subtle gravitational lensing of countless galaxies, using their distorted light to map the dark matter, scaffolding that underpins the entire structure in three-dimensional detail that is currently unimaginable. The Rubin Observatory won't just give us a sharper picture, it will give us a living one, revealing the pulse of the cosmos. Meanwhile, floating in the cold, stable darkness of space far beyond Earth's shimmering atmosphere, the Euclid Space Telescope is embarking on its own grand survey. Euclid's mission is to confront the deepest mystery of all dark energy. This is the enigmatic force that is causing the expansion of the universe to accelerate a cosmic anti-gravity that is slowly stretching the web apart. By meticulously mapping the positions and shapes of billions of galaxies over a vast swath of the sky, Euclid will study the web's structure at different epochs in cosmic history. It will see how the cosmic tug-of-war between the clumping force of gravity which builds the web and the repulsive force of dark energy which tears it asunder has evolved over billions of years. The very geometry of the web, the size of its voids, and the density of its clusters holds the key. Euclid is reading the history of cosmic expansion in the very architecture of the universe itself. Joining this quest is the Nancy Grace Roman Space Telescope, NASA's next great observatory. With a field of view 100 times larger than Hubble's Roman, will be a true wide-angle surveyor of the heavens. Peering deep into the infrared, it will be able to see through the veils of cosmic dust that obscure our view, capturing images of galaxies that are older, fainter, and more distant than ever before. It will provide a crucial piece of the puzzle, the adolescent years of the cosmic web. Roman will map the structure as it existed when the universe was just a few billion years old, a critical period when the web was still rapidly assembling and galaxy formation was at its most frenzied. This will bridge the gap between the mature web we see today and its earliest formative stages. But perhaps the most profound leap forward will come not from what we see, but from what we hear. The Square Kilometre Array, an intercontinental radio telescope being built in Australia and South Africa, will be the largest scientific instrument ever constructed on Earth. It will not be looking for the light from stars or galaxies. Instead, it will be listening for the faint whisper-thin radio waves emitted by neutral hydrogen gas. This hydrogen is the most abundant element in the universe, the raw, unprocessed fuel from which everything else is made. It is the very substance of the cosmic web's filaments, most of which is too dark and diffuse to be seen directly. The sky will have the sensitivity to tune into the 21-centimetre wavelength of this primordial gas, and in doing so, it will map the cosmic web in its purest, most fundamental form. It will be like switching from seeing the lights of cities at night to seeing the entire underlying geography of the continents themselves. We will no longer be inferring the presence of filaments by the galaxies they host. We will be imaging the vast flowing rivers of gas directly. This revolutionary technique will allow us to chart the web's tendrils all the way back into the cosmic dark ages, the era before the first stars ignited to see the web's initial seeds as they first began to sprout in the infant universe. With these new eyes and ears, we stand on the precipice of creating a map so complete, so detailed, that it will encompass nearly the entire history and volume of the visible cosmos. This relentless quest to chart the universe, may seem abstract, a grand intellectual exercise in cosmic geography, but its implications reach down from the largest scales imaginable to touch the very essence of our own existence. The cosmic web is not merely a magnificent structure out there. It is the incubator that made you possible. Think of the journey of the elements that form your body, the carbon in your cells, the oxygen. You breathe the iron in your blood. None of it was created in the Big Bang. It was all forged in the fiery hearts of stars and blasted out into space in violent supernova explosions. But what happened next? Where did this precious life-giving material go? This map gives us the answer. This stardust did not simply disperse aimlessly into the void. It was caught in the great gravitational currents of the cosmic web. It was swept along the filaments channeled down these celestial rivers for millions of light years and delivered into the swirling nurseries of new-forming galaxies like our own Milky Way. These filaments acted as a cosmic transportation network, concentrating the chemical building blocks of life into the exact places where the next generation of stars and planetary systems would form. Without this grand organizing architecture, the elements necessary for life might have been diluted into oblivion, spread too thinly across the expanding universe to ever coalesce into planets, let alone people. The web provided the structure, the conduits, the very framework for cosmic chemistry to unfold. It created the stable, long-lived galactic environments where planets could form and life could have a chance to emerge. In a very real sense, the skeleton of the universe is what allows for the possibility of its consciousness. This realization offers a tantalizing new guide in our search for life elsewhere. If the web's filaments are the supply lines for the ingredients of life, then the most fertile ground, the most promising places to look for other worlds teeming with biology, may lie within the great galactic clusters that form at the web's major intersections. These are the places where cosmic material has been most efficiently gathered and processed over billions of years. By understanding the flow of matter through this network, we are not just mapping the cosmos, we are creating a treasure map for astrobiology, identifying the most likely oases of life in the cosmic desert. The largest structure in the universe is inextricably linked to the search for the smallest microbes, and so we find ourselves here at the end of this journey, looking back at the path we have travelled. From a dark sky pricked with disconnected lights to a universe revealed as a single coherent, breathtaking whole. We are a species of map makers driven by an insatiable need to understand our surroundings, to know where we are. We have charted our planet, our solar system, our galaxy. And now we have drawn the first strokes of a map that contains all the others. This is the ultimate context, the final, "you are here" sign on the scale of reality itself. But the most profound revelation of this map is not about location, but about connection. It shows us in the most powerful way imaginable that the ancient human feeling of being small and isolated in the cosmos is a profound mistake. We are not insignificant specks lost in a meaningless void. Our Milky Way galaxy is not an isolated vessel sailing through an empty ocean. It is a traveller on a great celestial highway, part of a local filament that is flowing toward the Virgo cluster, which is itself being pulled toward the Great Attractor, a massive node in the cosmic web. Our entire existence is one of motion and belonging within this grander structure. The atoms that make you you have participated in this cosmic dance for eons, journeying through the web to arrive here on this planet at this moment, to contemplate their own origins. You're not just an observer of the universe, you're a temporary thinking, feeling, wondering piece of the cosmic web itself. You're its stardust animated by its chemistry and shaped by its laws. The structure that spans billions of light years is the very same structure that enabled your existence. There is no separation. We are not looking at a map of something external to us. We are looking at our own family tree traced back to the beginning of time and scaled to the edge of space. We are not lost in the darkness between the stars. We are home, an integral part of its fabric woven into the magnificent, luminous and unending cosmic web.